Look up at the night sky, and you'll see countless stars twinkling in the vast expanse, but just beyond what the naked eye can perceive lies something far stranger. A cosmic neighbor cloaked in mystery where the laws of physics twist into surreal spectacles and the universe reveals its most bewildering secrets. This is the Large Magellanic Cloud, a dwarf galaxy dangling right on our cosmic doorstep, and it's anything but ordinary. Imagine a place where stars vanish without a trace, where ghostly ribbons of gas glow with unseen energy, and where entire clusters of celestial objects defy everything we think we know about space. This isn't science fiction, it's reality, unfolding in a galaxy so close we can almost reach out and touch it. What makes the Large Magellanic Cloud so fascinating isn't just its proximity, it's the sheer volume of unexplained phenomena crammed into its shimmering depths. From explosive stellar disappearances to rogue black holes lurking in the shadows, this galaxy is a treasure trove of cosmic oddities that leave even the most seasoned astronomers scratching their heads. Think about it, a single dwarf galaxy, barely a fraction the size of our Milky Way, packed with more strangeness than we've catalogued in entire swaths of the universe. And today, we're diving deep into 30 of its most jaw-dropping enigmas, each one more mind-bending than the last. This journey isn't just about listing bizarre occurrences, it's about unraveling the stories behind them. Every unexplained flash, every eerie distortion of light, every inexplicable void in the fabric of space, they're all clues to a bigger puzzle. One that challenges our understanding of how galaxies form, how stars live and die, and what forces might be at work in the cosmos that we haven't even begun to comprehend. So if you've ever stared at the night sky and wondered what's really out there beyond the familiar constellations and distant planets, then buckle up. Because the Large Magellanic Cloud is about to take you on a ride through the weirdest corners of space, where the ordinary becomes extraordinary and the impossible might just be real. Deep within the Large Magellanic Cloud, a chaotic stellar nursery pulses with violent beauty, the Tarantula Nebula. It's a place where stars aren't just born, they erupt into existence with such ferocity that they carve gaping holes in the fabric of space itself. These aren't mere pockets of emptiness, they're superbubbles, colossal cavities stretching hundreds of light years across, forged by the relentless onslaught of stellar winds and cataclysmic supernova. Imagine a cosmic sculptor chiseling away at the nebula's swirling gases, leaving behind hollowed-out voids so vast they could swallow entire solar systems without a trace. What makes these superbubbles truly extraordinary isn't just their size, it's the way they rewrite the rules of interstellar physics. When massive stars ignite within the Tarantula Nebula, they don't just burn quietly. They unleash hurricane-force stellar winds, streams of charged particles moving at millions of miles per hour. Over time, these winds push outward, sweeping up surrounding gas like a snowplow clearing a highway. But the real destruction comes later, when the most massive stars reach the end of their lives in spectacular supernova explosions. The shock waves from these detonations slam into the already stretched gas, inflating the cavities even further, like a balloon repeatedly hit with bursts of compressed air. Here's where things get strange. These superbubbles shouldn't exist, at least, not the way we're seeing them. Current models predict that the energy from stellar winds and supernova would dissipate long before carving out such enormous structures. Yet somehow, the Tarantula Nebula's superbubbles defy expectations, growing larger and more complex than theory allows. Some astronomers suspect hidden forces might be at play, perhaps undiscovered types of energy transfer between stars and gas, or even the influence of rogue magnetic fields twisting through the nebula like invisible fingers. Whatever the cause, these superbubbles are forcing scientists to rethink how matter behaves in the most extreme environments of the universe, and the implications ripple far beyond this single nebula. If superbubbles can grow this large, this fast, they might be the universe's ultimate sculptors, reshaping galaxies by redistributing gas, triggering new waves of star formation, or even preventing it entirely in some regions. Picture a cosmic domino effect. One generation of stars dies in flames, blowing open gaps that dictate where the next generation can or can't be born. The Tarantula Nebula's violent artistry might hold the key to understanding why galaxies like our own Milky Way look the way they do. So the next time you gaze at the night sky, remember, even in the silence of space, there's a constant, thunderous roar of creation and destruction, and it's happening just next door in the Large Magellanic Cloud. Hidden in the depths of the Large Magellanic Cloud, a silent predator lurks, one so massive it bends the very fabric of space around it, yet remains utterly invisible to the naked eye. This is LMC X-3, a binary system where a black hole 10 times heavier than our Sun feasts on its helpless stellar companion, and the cosmic drama unfolding there is rewriting what we know about these dark giants. Picture a dance of death playing out across the void. A brilliant blue star, 20 times more massive than our Sun, orbits something unseen at breakneck speeds, circling so close that the black hole's gravity strips away its outer layers like a relentless thief. The stolen gas doesn't just vanish, it spirals into an accretion disk, superheated to millions of degrees before disappearing past the event horizon. This process should be predictable, steady, like a cosmic hourglass slowly draining. But LMC X-3 defies expectations. Instead of a constant stream of X-rays, the telltale scream of infalling matter. The system flickers unpredictably, flaring and fading in ways no model can fully explain. What makes these X-ray fluctuations so baffling isn't just their irregular rhythm. It's the sheer intensity of the changes. At times, the system dims to near darkness for months, as if the black hole suddenly loses its appetite. Then, without warning, it erupts in violent bursts of energy, shining hundreds of times brighter than before. Some astronomers suspect the companion star's powerful stellar winds might be clumping unevenly, creating temporary feasts and famines for the black hole. Others wonder if the accretion disk itself is warping under extreme magnetic fields, choking off the flow of matter in strange cycles, even more puzzling. This black hole is unusually quiet for its size. Most monsters this massive should be surrounded by swirling debris and radiation, yet LMC X-3 often lingers in eerie silence. It's as if the black hole is toying with us, offering glimpses of its feeding habits, then vanishing into shadow before we can fully understand the rules of the game. The implications stretch far beyond this single system. If black holes like this one behave in ways our models can't predict, what else might we be missing? Could entire populations of these hidden giants exist, flickering in and out of visibility across the cosmos? The Large Magellanic Cloud's enigmatic predator isn't just a curiosity. It's a challenge to everything we thought we knew about how black holes grow, feed, and reshape their corner of the universe. And with every erratic pulse of X-rays, it whispers a tantalizing question. Are we watching a cosmic aberration or just beginning to see how black holes truly work? 5,000 years ago, a star in the Large Magellanic Cloud met its explosive end not with a whimper, but with a scream that still echoes across space. Today, we see its ghostly remains as LMC X-49, a supernova remnant glowing with tangled filaments that stretch over 150 light-years. Unlike typical remnants that fade into faint wisps, this cosmic wreckage pulses with an eerie energy, threaded by magnetic fields so intense they could rearrange atoms on contact. What catches scientists off guard isn't just the remnants' haunting beauty, it's the bizarre behavior of those magnetic fields. Normally, supernova remnants scatter their magnetic forces chaotically, like a shattered mirror reflecting light in every direction. But LMC X-49 defies the rules. Its fields align in bizarre, concentrated ropes, some 1,000 times stronger than Earth's magnetic field, twisting through the gas like celestial jail bars. One theory suggests the original star might have spun so fast before its death that its core became a dynamo, amplifying magnetic energy exponentially in its final moments. When the star detonated, those hypercharged fields didn't dissipate. They embedded themselves into the expanding debris like invisible tattoos, even more compelling. The remnants' X-ray glow hints at an unseen prisoner lurking within. Deep in the wreckage, astronomers detect rhythmic bursts of high-energy radiation, too precise to be random turbulence. This ticking signal has led some to speculate that the supernova left behind something far stranger than a typical neutron star, a magnetar, a city-sized remnant with a magnetic field so powerful it could erase credit cards halfway across the galaxy. These ultra-dense objects are so rare that spotting one in our cosmic backyard would rewrite what we know about stellar deaths. Yet LMC X-3 keeps its secrets close. The magnetar, if it exists, remains hidden beneath layers of glowing debris, its presence only betrayed by flickers of radiation. Some researchers propose an even wilder scenario. Perhaps we're witnessing the birth of something unprecedented. A new class of object forged in the heart of a supernova so peculiar that it left behind a hybrid remnant, part magnetar and part nebula. Every new observation peels back another layer, proving that even in death, stars can still surprise us. This 5,000-year-old cosmic crime scene isn't just a relic, it's an active laboratory. The way its magnetic fields interact with speeding particles could reveal how supernovas seed galaxies with the building blocks for new stars and planets. And if that hidden magnetar is real, it might teach us why some dying stars leave behind these magnetic monsters while others fade quietly into the dark. LMC X-3's ghostly glow isn't just a memorial, it's a message written in the twisted language of physics, waiting for us to decipher it. Some stars in the Large Magellanic Cloud don't just drift peacefully through space. They flee like cosmic fugitives, racing across the galaxy at speeds that defy logic. Take E04375439, a massive blue star hurtling away from its home at 2.6 million kilometers per hour, so fast it could cross the distance from Earth to the Moon in just 6 minutes. This isn't just motion, it's an escape so violent it challenges our understanding of stellar dynamics. How does a star reach such impossible speeds? The leading theory points to a cosmic slingshot maneuver near the galaxy's central supermassive black hole. Picture this, once part of a binary star system, E04375439, and its companion wandered too close to the gravitational monster. As tidal forces ripped the pair apart, one star fell into the black hole's clutches while the other was flung outward like a stone from a catapult, gaining enough velocity to break free from the galaxy entirely. The energy required for this ejection is staggering, equivalent to hundreds of supernovae channeled into a single, precise kick. But here's the twist, this star's composition doesn't quite fit the narrative. Spectroscopic analysis reveals it's around 35 million years old, far younger than the travel time needed to reach its current position if launched from the LMC's center. This discrepancy has astronomers questioning everything. Could the star have formed differently, perhaps in a dense cluster where multiple black hole interactions supercharged its speed? Or might we be seeing evidence of an entirely new ejection mechanism? One involving intermediate mass black holes we haven't yet detected. The implications ripple across cosmology. If stars can achieve such velocities through these chaotic interactions, they become intergalactic travelers, seeding heavy elements across the void and potentially even triggering star formation in other galaxies. E04375439 isn't just running. It's carrying the chemical fingerprints of its birthplace into uncharted territories. And as we watch its desperate flight, we're left wondering how many other celestial runaways might be streaking through the darkness, carrying untold stories of cosmic violence in their wake. The Large Magellanic Cloud holds a gravitational secret, one that lurks invisibly, shaping the motion of stars and gas in ways that shouldn't be possible. While most galaxies, including our Milky Way, wrap their dark matter in predictable halos, the LMC's unseen mass appears to clump unevenly, like shadowy islands scattered across a cosmic archipelago. This bizarre distribution could rewrite our playbook on how dark matter behaves in smaller galaxies. Current models suggest dark matter should envelop dwarf galaxies smoothly, thinning out gradually from the core. Yet when astronomers mapped the LMC's gravity by tracking the frenetic orbits of its star clusters and gas clouds, they found startling inconsistencies. Certain regions exerted far stronger gravitational tugs than expected, as if pockets of invisible matter were densely packed in specific zones while other areas remained eerily vacant. One particularly baffling void lies near the galaxy's outskirts, where stellar motions imply a shocking absence of dark matter altogether. It's like finding a stretch of ocean where water mysteriously refuses to flow. What could cause such patchiness? One radical theory points to an ancient collision. Billions of years ago, the LMC might have sideswiped another dwarf galaxy, its gravitational turbulence scattering dark matter like crumbs off a shaken table. Alternatively, the dark matter itself could possess properties we've yet to understand, perhaps interacting with itself through unknown forces that cause it to clump unpredictably. The most tantalizing possibility that we're seeing signs of dark matter substructure, tiny dense nuclei within the halo that current telescopes can't directly detect. This isn't just academic curiosity, it's a potential paradigm shift. If dark matter organizes differently in small galaxies, it could explain why the LMC hosts such extreme star-forming regions. Those invisible mass concentrations might compress gas clouds, triggering stellar births in erratic bursts. Even more compelling, the LMC's strange gravity could hint at dark matter's true nature. Is it cold and sluggish as most theories assume, or does some component move fast enough to escape certain areas, leaving gravitational gaps? Every unaccounted wobble in a star's path, every inexplicable warp in a gas cloud's movement, they're cosmic breadcrumbs leading us closer to dark matter's secrets. And the Large Magellanic Cloud, with its defiantly irregular gravity, might just hold the key to unlocking them. In the cosmic theater of the Large Magellanic Cloud, some stars don't just bow out gracefully, they stage elaborate fake deaths, leaving astronomers utterly fooled. Take SN 2009 IP and SN 1961V, two stellar enigmas that pulled off the universe's most convincing supernova impersonations. These weren't just brief flashes in the dark, they were full-blown cosmic performances, complete with violent eruptions and dazzling light shows that mirrored real stellar explosions down to the smallest detail. Yet when the smoke cleared, both stars were still standing, rewriting the rules of how massive stars behave in their final years. SN 2009 IP first grabbed attention when it brightened suddenly in 2009, belching out enough material to rival a prelude to destruction. For 3 years, it flickered unpredictably, flaring, dimming, then flaring again before unleashing a cataclysmic explosion in 2012 so bright it outshone its entire host galaxy. Telescopes caught every detail, shockwaves rippling through ejected gas, temperatures spiking to millions of degrees, even the telltale chemical signatures of a dying star. By all accounts, this should have been a supernova's final act, yet months later the star was still there, diminished, wounded, but undeniably alive. Then there's SN 1961V, the original supernova imposter. Observed 6 decades ago, this star's outburst was so extreme it briefly outshone every other object in the LMC. For months, it radiated with the energy of a true supernova, ejecting shells of material that expanded at terrifying speeds. Astronomers classified it as a textbook core collapse event until decades later, when deep imaging revealed the unthinkable. The star hadn't died at all. It had somehow survived its own apparent apocalypse, fading back into obscurity like a cosmic phoenix that forgot to burn. What makes these imposters so baffling isn't just their resilience, it's how perfectly they mimic genuine supernova. Both events showed all the hallmarks of stellar death: sudden brightening, ejected material rich in heavy elements, even the correct light curves over time. Yet beneath the spectacle, something entirely different was happening. Rather than collapsing inward, these stars may have experienced extreme eruptions, violent surface convulsions that flung off outer layers while leaving their cores intact. Imagine a volcano ejecting enough lava to look like an entire mountain exploding, only for the summit to remain standing. The implications are profound. If stars can fake their own deaths this convincingly, how many historical supernovae in our records might actually be survivors? Some researchers now suspect these imposters represent a rare transitional phase, a star's last desperate attempts to stabilize before true collapse. Others propose their evidence of exotic stellar physics, where twin stars in close orbits trigger periodic eruptions through gravitational tugs of war. One thing's certain: every imposter we discover forces us to redraw the line between stellar tantrums and true cosmic demise. Perhaps most thrilling is what these events reveal about stellar mortality. Traditional models paint massive stars' deaths as straightforward sequences: run out of fuel, collapse, explode. But SN 2009 IP and SN 1961 V prove stars can cheat death, at least temporarily, through mechanisms we're only beginning to grasp. Their existence suggests the final stages of stellar evolution might be far messier, far more unpredictable than we ever imagined. And in the tangled stellar nurseries of the Large Magellanic Cloud, who knows how many other cosmic actors are waiting to take the stage, not for their final bow, but for an encore that defies all expectations. Nestled in the heart of the Tarantula Nebula, the R136 star cluster glows like a cosmic crown jewel, but its brilliance comes from a collection of stellar titans so massive they shouldn't exist. This compact swarm of stars houses some of the most extreme objects ever recorded, including R13601, a blue hypergiant so colossal it weighs in at over 250 times the mass of our Sun. That's not just big, it's a direct challenge to everything we thought we knew about how stars are born. Current stellar formation theories hit a hard ceiling at around 150 solar masses. Beyond that, the physics should break down. As a protostar grows, its own radiation pressure ought to blow away the surrounding gas before it can accumulate more mass. It's like trying to fill a bucket with water while standing in a hurricane. The sheer force of the star's energy should prevent further growth. Yet R136's monsters laugh in the face of these limits, suggesting either our models are missing something fundamental, or the conditions in this cluster are unlike anything else in the known universe. One clue might lie in the cluster's extreme density. Packed into a region just a few light years across, these stars orbit so close that their gravitational interactions could have played a role in their formation. Some astronomers propose a process called competitive accretion, where stars in tight formations steal material from each other in a cosmic feeding frenzy. Picture a group of stellar embryos wrestling over the same gas cloud, with the most aggressive ones gorging themselves into unprecedented sizes. Others suggest these behemoths might actually be the products of stellar mergers, smaller stars colliding and fusing in the cluster's chaotic early days. But the anomalies don't stop at their birth. These stars burn so ferociously that they defy predictions about their lifespans. A star of 250 solar masses should theoretically tear itself apart in just a few million years, yet R13601 shows unexpected stability. Its surface blazes at over 50,000 degrees Celsius, driving stellar winds so powerful they eject an Earth's worth of mass every month. Somehow, against all odds, it maintains equilibrium, a balancing act between gravity's inward crush and radiation's outward fury that we've yet to fully decipher. Then there's the radiation environment. The combined ultraviolet output of R136's giants is so intense it ionizes gas clouds 40,000 light-years away, sculpting the surrounding nebula into surreal shapes. This isn't just starlight, it's a cosmic blowtorch, redefining its corner of the universe with sheer radiative force. The cluster's collective energy output is millions of times brighter than our Sun, creating conditions so extreme they mimic the early universe's most violent stellar nurseries. What makes R136 truly revolutionary isn't just its record-breaking stars, it's the window it provides into stellar evolution's outer limits. These hypergiants likely end their lives not as typical supernova, but as pair instability explosions, cataclysms so violent they leave no black hole behind, just a void where a star once stood. Studying them now gives us front-row seats to processes normally restricted to the universe's first billion years, when behemoth stars supposedly dominated the cosmos. The implications ripple across astronomy. If stars can form this massive in the LMC, might the early universe have spawned even larger ones? Could some of the distant, unexplained cosmic explosions we detect be these rare monsters meeting their fiery ends? R136 doesn't just challenge textbooks, it tears them up, forcing us to rewrite the rules of stellar physics with every new observation. And as we stare into this stellar crucible, we're left with a humbling thought. The universe's most extreme laboratories might be closer than we ever imagined. Galaxies come in predictable shapes, spirals with graceful arms, ellipticals like glowing orbs, and irregulars with chaotic structures. So why does the Large Magellanic Cloud, a textbook irregular dwarf galaxy, suddenly sprout spiral arms when viewed through certain telescopes? This isn't just a minor oddity. It's a cosmic identity crisis, one that might trace back to a violent encounter with its sibling galaxy millions of years ago. At first glance, the LMC appears exactly as expected, a messy, asymmetrical blob of stars and gas. But switch to infrared or radio wavelengths, and an entirely different structure emerges, faint yet unmistakable spiral arcs curving through its disk. These aren't the grand, symmetrical arms of galaxies like Andromeda. They're mangled and fragmentary, like the ghostly afterimage of a structure that wasn't supposed to exist. For an irregular galaxy, which by definition lacks organized features, this is like finding a snowflake in a sandstorm. The leading explanation points to a gravitational run-in with its neighbor, the Small Magellanic Cloud. Computer simulations suggest these two galaxies may have skimmed past each other around 200 million years ago, cosmically recent by galactic standards. When galaxies interact, their mutual gravity can trigger density waves that ripple through their gas clouds, compressing material into temporary spiral patterns. Normally, this happens to grand spirals, not tiny irregulars like the LMC. Yet somehow, the encounter left behind these phantom arms, frozen in time as they gradually unwind. Here's where things get stranger. The spiral features appear almost exclusively in cold hydrogen gas, not in the distribution of stars. It's as if the gravitational disturbance only managed to organize the galaxy's lightest, most diffuse material while leaving the stellar population untouched. This selective structuring hints at something fundamental about how galaxies respond to collisions, that gas and stars might react differently to the same gravitational forces. Imagine shaking a snow globe and watching the glitter form perfect spirals while the heavier flakes remain in chaos. But the plot thickens when we examine the arm's chemistry. The gas within these spiral arcs shows unusual metallicity levels higher than expected for the LMC's outer regions. One provocative theory suggests the Small Magellanic Cloud didn't just distort the LMC's shape during their encounter. It might have stripped away some of its own gas, depositing chemically enriched material into these emerging structures. If true, these spiral arms aren't just gravitational artifacts. They're cosmic fingerprints preserving evidence of intergalactic theft on a staggering scale. The implications stretch far beyond these two galaxies. If even irregular dwarfs can temporarily mimic spirals after collisions, it suggests galaxy classification might be more fluid than we thought. Perhaps all galaxies, no matter their current shape, carry echoes of past encounters in their structure, visible only to those who know where to look. The LMC's hidden arms serve as a reminder that in the cosmos, first impressions often deceive, and sometimes the most revealing details emerge only when we shift our perspective. Amid the cosmic chaos of the Large Magellanic Cloud, one object spins with such mechanical precision and such baffling unpredictability that it could be the universe's most accurate clock. If it didn't keep breaking its own rhythm, meet pulsar J0537-6910, a neutron star rotating at a staggering 62 times per second, flashing its lighthouse-like beam across the galaxy with metronomic regularity. But here's the catch: without warning, this cosmic timekeeper suddenly violently speeds up. These aren't tiny hiccups, they're full-blown glitches where the pulsar's spin lurches forward as if kicked by an invisible hand, gaining hundreds of extra rotations in mere seconds before settling back into its usual rhythm. And with each erratic jump, it chips away at our understanding of how neutron stars actually work. What makes J0537-6910 so extraordinary isn't just the frequency of its glitches, it's their sheer predictability amidst the chaos. Unlike other glitching pulsars that stutter randomly, this one throws a tantrum roughly every 2.6 million rotations like clockwork. Imagine a precision watch that keeps perfect time. Except every hour, its second hand suddenly races ahead 5 minutes before snapping back to normal. This bizarre regularity has astronomers scratching their heads. Most pulsar glitches are thought to stem from starquakes, sudden cracks in the neutron star's rigid crust caused by its mind-bending density. But J0537-6910's glitches are too frequent, too uniform for that explanation to hold. The leading theory involves vortices, tiny whirlpools of superfluid neutrons swirling beneath the pulsar's crust. Normally, these vortices align with the star's rotation, locked in place by quantum forces. But as the pulsar slows over time, losing energy through radiation, the vortices occasionally break free, transferring angular momentum to the crust like a spinning ice skater pulling their arms in. Here's the twist. J0537-6910's glitches release 10 times more energy than typical pulsars, suggesting something far more violent is at play. Some researchers speculate its interior might harbor pockets of exotic matter, perhaps free-floating quarks not bound into neutrons sloshing against the crust with enough force to torque the entire star. Even weirder, this pulsar lives inside N157b, a supernova remnant still glowing from the explosion that birthed it. The remnant's intense radiation field should, in theory, be slowing the pulsar down faster than observed. Yet J0537-6910 maintains its spin with eerie defiance, as if drawing energy from its surroundings. Could it be siphoning material from the remnant's debris, or are we seeing evidence of a magnetic field so complex it's generating additional torque? Every glitch leaves behind forensic clues, tiny changes in spin rate, thermal emissions, even X-ray flares, that might reveal the pulsar's inner workings. The stakes couldn't be higher. If we crack J0537-6910's code, we're not just solving one pulsar's mystery, we're peering into the quantum heart of matter itself. Neutron stars are nature's ultimate physics labs, compressing conditions impossible to replicate on Earth. Each glitch is a telegram from this extreme realm, carrying data about how matter behaves under pressures that crush atoms into surreal new forms. And tucked within the Large Magellanic Cloud, this cosmic rebel isn't just breaking the rules, it's daring us to rewrite them. In the swirling chaos of the Large Magellanic Cloud, two cosmic beacons pulse with an otherworldly glow, not in visible light but in the microwave spectrum. N113 and N159 aren't just nebulae, They're megamasers, nature's most powerful lasers, stretching across distances so vast they could swallow our entire solar system without a trace. Unlike the lasers we create in labs, these aren't beams of focused light, they're natural amplifiers, turbocharged by some of the most violent star-forming regions in the known universe. What makes these megamasers so extraordinary is their fuel, molecules of water and hydroxyl, shaken by the furious energy of newborn stars. Picture a cloud of gas where every droplet hums in perfect synchronization, amplifying microwave radiation into coherent beams millions of times brighter than anything possible in interstellar space. The conditions have to be just right: crisp temperatures just above absolute zero, densities precise enough to excite molecules without tearing them apart, and an energy source powerful enough to keep the whole system pumping. It's like balancing a house of cards in a hurricane, yet N113 and N159 pull it off with eerie perfection. But these megamasers aren't just cosmic curiosities, they're measuring sticks for the universe. Because their microwave emissions are so consistent, astronomers can use them as precise distance markers. Here's how it works. As the LMC moves through space, the megamaser beam's Doppler shifts slightly, revealing the galaxy's velocity relative to Earth. But the real magic happens when scientists compare these velocities to the galaxy's apparent motion across the sky. That tiny parallax, the way the masers appear to shift against more distant background objects, lets researchers triangulate the LMC's distance with astonishing accuracy. It's celestial trigonometry on an intergalactic scale, with megamasers as the guiding beacons. The strangest part, these microwave lasers shouldn't be here at all. Megamasers typically form in the dusty hearts of distant galaxies, where supermassive black holes pump energy into surrounding gas. But the LMC's versions are different. They're powered purely by stellar fury. N159, for example, sits in the heart of the Tarantula Nebula, a star factory so intense it's birthing stars 50 times heavier than our Sun. The radiation from these stellar titans excites surrounding water molecules, turning the entire nebula into a natural amplifier. It's as if the universe handed us a flashlight in the cosmic dark, saying, "Here, use this to map the void." Yet, even as they illuminate the cosmos, these megamasers guard their own secrets. N113 flickers unpredictably, its microwave output surging and fading in ways that defy current models. Some researchers suspect hidden stellar collisions or rogue black holes might be stirring the molecular soup, creating chaotic feedback loops. Others wonder if we're seeing the fingerprints of exotic chemistry, rare molecular transitions that only occur under these extreme conditions. Every pulse from these megamasers carries more than just distance data. It's a snapshot of the LMC's turbulent soul, a reminder that even in the cold expanse of space, nature finds ways to create order from chaos. And as we listen to their microwave whispers, we're not just measuring the universe, we're decoding the hidden rhythms of star birth itself. Globular clusters should be the elder statesmen of any galaxy, dense, spherical collections of ancient stars that formed in the universe's turbulent infancy. Yet when astronomers peer into the Large Magellanic Cloud, they find a glaring cosmic census discrepancy. This galaxy holds barely a handful of these stellar fossils, a fraction of what similar dwarf galaxies typically possess. Where did they go? The answer might rewrite our understanding of galactic survival tactics. Most galaxies the size of the LMC host dozens of globular clusters, remnants of the earliest star-forming frenzy after the Big Bang. Our own Milky Way boasts over 150, but the LMC just 15 confirmed, with some so sparse and disrupted they barely qualify. This scarcity is even stranger when you consider the galaxy's age. It's been around long enough to have formed hundreds. One theory suggests the LMC never had many to begin with. Unlike larger galaxies that grew by cannibalizing smaller neighbors, inheriting their globular clusters in the process, the LMC might have led a quieter existence, missing out on these cosmic acquisitions. But the plot thickens when we examine the survivors. The LMC's remaining globular clusters aren't just rare, they're weirdly youthful compared to their Milky Way counterparts. Spectroscopy reveals many formed only 6 to 8 billion years ago, eons after the universe's first wave of cluster formation. This implies something dramatic happened, a delayed starburst event that somehow triggered a second generation of clusters. Perhaps a close encounter with the small Magellanic Cloud stirred the galaxy's gas, compressing it into new star-forming pockets. Or maybe the LMC's turbulent history included phases where it lost and then regained star-forming material, creating episodic bursts of cluster births. The most provocative explanation: the missing clusters weren't lost, they were destroyed. The LMC's gravitational dance around the Milky Way subjects it to brutal tidal forces. Over billions of years, these forces could have shredded fragile globular clusters, stretching them into stellar streams that eventually dissolved into the galaxy's halo. Computer simulations show this process in action. Clusters orbiting too close to the LMC's core get torn apart by gravitational shear, their stars scattered like sand in a cosmic whirlwind. Supporting this theory, the few surviving clusters mostly orbit far from the galaxy's center, where tides are weaker, yet there's a tantalizing alternative. Some researchers propose the LMC once had a normal complement of globulars until it passed through the Milky Way's dark matter halo. This invisible web of particles might act like interstellar sandpaper, stripping away loosely bound clusters through dynamical friction. If true, the LMC's missing clusters could be mapping unseen dark matter structures in our local group. The implications stretch far beyond one galaxy. If globular clusters are this fragile, they might serve as cosmic canaries, sensitive tracers of a galaxy's past collisions and close calls. Their absence in the LMC could be a footprint of ancient violence, a record of gravitational battles fought and lost. And as we study these gaps in the stellar record, we're left with a humbling realization. Sometimes what's missing tells us more than what remains. Most galaxies with central bars, including our Milky Way, feature quiet, aging stellar populations in these elongated structures. But the Large Magellanic Cloud defies expectations yet again, with its bar hosting a fireworks show of newborn stars that challenges everything we know about galactic anatomy. This isn't just a few scattered young stars, it's a full-blown stellar baby boom with massive blue stars lighting up the bar like a cosmic neon sign. How did this happen, and why doesn't our own galaxy's bar show the same youthful exuberance? The Milky Way's central bar behaves like a retirement home for stars packed with older, cooler red stars that formed billions of years ago. Gas and dust in this region rarely collapse into new stars, stabilized by the bar's intense gravitational forces. But the LMC's bar tells a different story entirely. Infrared surveys reveal vast molecular clouds threaded through its length, along with telltale traces of recent starbirth like glowing hydrogen regions and clusters of luminous O-type stars less than 10 million years old. It's as if someone injected the galactic equivalent of fertility drugs into this structure, triggering star formation where theory says it shouldn't thrive. One clue lies in the LMC's chaotic dance with the small Magellanic Cloud and Milky Way. Galactic interactions can funnel gas toward central bars, compressing it until it ignites into new stars. But the real game changer might be the bar's unusual composition. While most galactic bars consist primarily of stars, the LMC's contain staggering amounts of cold molecular gas, up to 30% of its total mass. This reservoir of star-forming material constantly refreshes itself, possibly through gas clouds being stripped from the galaxy's outer regions and driven inward by tidal forces. The dynamics get even stranger when you examine where the star formation occurs. Instead of being evenly distributed, young stars cluster along the bar's leading edges, the sides facing the direction of rotation. This suggests the bar might be plowing through interstellar gas like a snowplow, piling up material until it reaches critical density. Supporting this view, the bar's youngest stars align almost perfectly with dust lanes visible in radio telescopes, tracing the shock fronts where gas clouds collide and collapse. What makes this phenomenon truly bizarre is the timescale. Starburst events usually last a few tens of millions of years before exhausting their fuel. Yet evidence suggests the LMC's bar has been forming stars continuously for at least 500 million years, an eternity by cosmic standards. This endurance might come from the bar's unique ability to recycle material. Supernova from its massive young stars blast heavy elements back into surrounding gas, enriching future generations of stars in an ongoing cycle of creation and destruction. The contrast with our Milky Way's bar couldn't be sharper. While both structures likely formed through similar gravitational instabilities, the Milky Way's bar stabilized long ago, its gas either consumed or blown away by ancient starbursts. The LMC's bar remains a dynamic, ever-changing engine of creation, perhaps because as a smaller galaxy, it never reached the equilibrium of its larger cousins. Every new star cluster born there is a reminder that galaxies don't always play by the same rules, and that sometimes the most fascinating cosmic stories unfold where we least expect them. Stretching across 1,000 light-years of space, the great LMC supergiant shell isn't just another cosmic bubble, it's a sprawling, dynamic arena where death and birth collide on an unimaginable scale. Picture a soap bubble blown by giants, its surface shimmering with newborn stars while its cavernous interior echoes with the ghosts of ancient supernova. This colossal structure, catalogued as LMC4, began forming 30 million years ago when generations of massive stars reached the end of their lives in rapid succession, not with whimpers but with world-shattering blasts that carved out this gargantuan void. What sets this shell apart isn't just its size, it's the intricate ecology of destruction and creation happening within its walls. As each dying star exploded, its shockwave plowed through surrounding gas like a bulldozer, sweeping up material into dense, glowing ridges along the bubble's edge. These compressed walls became stellar maternity wards, where gravity takes the wreckage of dead stars and sculpts it into new ones. Infrared telescopes revealed dozens of protostars embedded in these filaments, some already glowing with the first flickers of nuclear fusion, while others remain cocooned in veils of dust, not yet ready to join the cosmic dance. The shell's anatomy tells a violent history. Spectral analysis of its gas reveals alternating layers of heavy elements: oxygen, neon, silicon, each representing a different supernova's explosive fingerprint. It's like counting tree rings, but instead of years, these strata mark successive waves of stellar death. The oldest material sits farthest out, testament to the earliest explosions that initiated the shell's expansion, while newer ejecta from more recent supernova lurk closer to the bubble's still active core. One particular region, LMC 4N19, shows such intense star formation that astronomers suspect it's where multiple shockwaves collided, piling gas upon gas until the density reached critical mass. Here's where physics gets weird. Normally, a supernova's shockwave should dissipate after a few 100,000 years, yet this shell's walls keep expanding at nearly 15 kilometers per second. The secret might lie in the sheer number of contributing stars. With over 40 confirmed supernova remnants embedded in its structure, LMC4 essentially receives a fresh kick of energy every few 100,000 years, like a car maintaining speed through constant bursts of acceleration. This staggered energy injection prevents the shell from stalling, allowing it to grow larger than any single explosion could achieve alone. But the real magic happens in the turbulence. As the shell expands, it doesn't move smoothly. It ripples and knots, creating pockets where gas densities vary wildly. These irregularities become stellar incubators, with some regions forming massive stars 10 times heavier than our Sun, while others spawn smaller, cooler stars. This diversity challenges traditional star formation theories, which assume relatively uniform conditions across a gas cloud. Instead, the Great Shell suggests that chaos might be the true midwife of stellar birth, with randomness playing a bigger role in a star's ultimate fate than we ever imagined. Perhaps most astonishing is the shell's long-term impact. As newborn stars within its walls ignite their fusion engines, their ultraviolet radiation ionizes surrounding gas, creating brilliant nebula patches that telescope surveys initially mistook for independent objects. Only recently did astronomers connect these glowing regions as parts of a single, interconnected structure. This means the Great Shell isn't just a relic, it's an active participant in the LMC's evolution, redistributing matter and energy across hundreds of light years. Future observations might reveal something even stranger, hints of triggered star formation outside the shell itself. Some models suggest the expanding wall could be sending secondary shockwaves into undisturbed gas beyond its boundary, potentially setting off new rounds of star birth like a cosmic domino effect. If confirmed, it would mean this single structure has been shaping stellar demographics across multiple generations, a celestial puppet master pulling the strings of creation, all from a bubble blown by the dying breaths of stars. Deep in the Large Magellanic Cloud, two cosmic powerhouses operate with the ferocity of supermassive black holes, but packed into bodies no larger than a city. LMC X-1 and LMC X-2 are microquasars, stellar mass black holes that somehow produce jets rivaling those from galactic cores millions of times more massive. These aren't just scaled-down versions of quasars, they're nature's most precise laboratories for studying relativistic physics, cramming all the violence of an active galactic nucleus into a package small enough to observe in exquisite detail. Take LMC X-1 first. This 20-solar mass black hole orbits a massive blue star, steadily siphoning off its companion's gas. As material spirals inward, it forms an accretion disk so hot it glows in X-rays, but the real show happens at the poles. Here, magnetic fields twist into coils so intense they launch jets of plasma at 90% light speed. These aren't gentle streams, they're narrow, focused beams stretching over 3 light years, punching through interstellar gas like cosmic blowtorches. What baffles scientists isn't just their existence, but their stability. Unlike the flickering jets of most microquasars, LMC X-1s remain steady for years, mirroring the behavior of far larger quasars despite having vastly weaker gravity to power them. Then there's LMC X-2, the wild sibling. While it shares the same basic blueprint, a black hole feeding on a companion star, its behavior couldn't be more different. Every few months, this system erupts in spectacular outbursts, its jets changing direction unpredictably as if guided by some unseen cosmic hand. During these events, X-ray emissions spike 100-fold, and radio telescopes catch ghostly afterimages of past jets fading into the void. The most compelling theory suggests LMC X-2's accretion disk might be warped, wobbling like a spinning top as it feeds the black hole unevenly. This instability could cause the jets to precess, tracing spirals in space that complicate our ability to model their behavior. What makes these systems so revolutionary is how they compress galactic-scale physics into observable packages. Quasars at the hearts of distant galaxies take millions of years to show meaningful changes, but LMC X-1 and LMC X-2 evolve over mere months. Watching their jets interact with interstellar material provides real-time demonstrations of how kinetic energy transforms gas clouds, how magnetic fields channel particles across light years, and how black holes recycle matter back into the cosmos. They're like cosmic DVD players set to fast forward, letting us watch processes that would otherwise take millennia unfold before our eyes, yet mysteries abound. How do these small black holes achieve jet efficiencies rivaling their supermassive cousins? Why does one exhibit quasar-like stability while the other behaves more like a strobe light? Some researchers speculate the answer lies in the black hole spin. LMC X-1 might rotate near the maximum possible rate, acting like a flywheel storing immense rotational energy. Others point to differences in their companion stars. LMC X-2's donor star is more erratic, possibly feeding chaotic bursts of material that disrupt the jet formation process. These twin microquasars offer more than just celestial spectacle. They're testing grounds for fundamental physics. Their jets generate conditions impossible to recreate on Earth, with magnetic fields strong enough to warp space-time and plasma temperatures exceeding 1 trillion degrees. By studying how particles accelerate in these extreme environments, physicists can probe questions about energy transport, relativistic motion, and even the nature of information itself. After all, what falls into a black hole might be lost forever, but its jets broadcast secrets about the abyss they sprang from. The greatest lesson might be one of scale. The universe doesn't care whether a black hole weighs 10 suns or 10 billion given the right conditions. The same physics can play out in vastly different arenas. And nestled in the Large Magellanic Cloud, these two miniature monsters prove that sometimes the most profound cosmic truths come in surprisingly small packages. Most galaxies spin like well-balanced tops, their axes of rotation neatly aligned with their paths through space. But the Large Magellanic Cloud spins sideways, a cosmic rebel twirling at a dramatic 45-degree angle to its orbit around the Milky Way. This isn't just a quirk of perspective, it's a fundamental defiance of how satellite galaxies should behave, and it's forcing astronomers to reconsider everything from dark matter's role to the violent history hidden in this dwarf galaxy's past. The mystery starts with basic expectations. When a smaller galaxy falls under a larger one's gravitational sway, tidal forces should eventually torque its rotation into alignment like a compass needle settling toward magnetic north. Given that the LMC has circled the Milky Way for billions of years, its stubborn tilt makes no sense. One leading theory suggests a catastrophic collision long ago, before the LMC became our galactic neighbor. If another dwarf galaxy slammed into it at just the right angle, the impact could have knocked the LMC's spin axis askew, leaving it forever tilted like a spinning top bumped off balance. Supporting this idea, the LMC's distorted shape and the strange motions of some outer star clusters, which show scars consistent with a violent merger. But there's a twist. Dark matter might be the invisible puppeteer behind this cosmic oddity. Unlike normal matter, dark matter doesn't interact with light or other particles. It only makes its presence known through gravity. Computer simulations show that if the LMC's dark matter halo is unusually lumpy or elongated, it could anchor the galaxy's rotation at this strange angle, resisting the Milky Way's attempts to straighten it out. Imagine a gyroscope wrapped in an invisible, asymmetrical web. No matter how you tilt the outer frame, the inner spin stays stubbornly offset. The implications reach far beyond this one galaxy. If the LMC's tilt stems from an ancient collision, it suggests dwarf galaxies were far more chaotic in the early universe, constantly smashing together in ways that left permanent scars. Alternatively, if dark matter's distribution is truly this irregular, it challenges our models of how this mysterious substance behaves on small scales. Every time we measure the motions of stars or gas clouds in the LMC, their paths trace the fingerprints of forces we're still struggling to understand, a reminder that even the closest galaxies guard secrets written in the language of gravity and spin. Perhaps most tantalizing is what this tilted rotation reveals about the LMC's future. That off-kilter spin creates dynamic friction as the galaxy plows through the Milky Way's halo, slowly sapping its orbital energy. Over billions of years, this could send the LMC spiraling inward until it merges with our galaxy, a fate its twisted rotation might have sealed long ago. So when we gaze at this lopsided whirl of stars, we're not just seeing a galactic oddity, we're witnessing the opening act of a cosmic dance that will reshape both galaxies in ways we're only beginning to predict. The 30 Nebula doesn't just sparkle with newborn stars. It roars with their fury, sending shockwaves through its cosmic seas that sculpt gas into towering waves stretching over 100 light-years. This isn't just a static celestial landscape. It's a dynamic battleground where stellar winds and supernova blasts collide with interstellar material, creating ripples so vast they could swallow entire solar systems. The result, a stellar tsunami, a phenomenon so violent it mimics Earth's ocean waves, if those waves were forged from plasma and moved at 500,000 miles per hour. At the heart of this chaos lies R136, the star cluster we met earlier, home to the most massive stars known. These celestial titans don't just burn, they rage, hurling out winds of charged particles with enough force to push surrounding gas into colossal crests and troughs. Picture a hurricane meeting a tidal wave, but on a scale where the waves themselves are light years high, and the energy driving them could power a star for millennia. The most dramatic structures form where these winds smash into denser gas pockets, creating shock fronts that glow in X-rays and infrared, visible as shimmering arcs through telescopes like Hubble and Chandra. But here's what makes this stellar tsunami truly bizarre. Its behavior defies simple fluid dynamics. On Earth, ocean waves dissipate as they break, their energy scattering into foam and spray. In 30 the waves actually grow more organized over time. Spectroscopic data reveals that some shock fronts propagate for thousands of years without losing coherence, their energy somehow replenished by new stellar outbursts or magnetic fields woven through the gas like invisible threads. One particularly striking filament, dubbed the Goldilocks wave, has maintained its structure for an estimated 20,000 years, a testament to the delicate balance between destruction and persistence in this nebula. The ripple effects extend far beyond visual spectacle. These shockwaves act as cosmic pressure cookers, triggering star formation in their wake. As they plow through the nebula, they compress gas to critical densities, forging new stellar nurseries even as they obliterate others. Some of the youngest stars in the LMC clusters, barely 1,000,000 years old, align perfectly with older shock fronts, as if the tsunami's fury wrote a roadmap for where the next generation would ignite. It's a stellar version of predator and prey, where the deaths of massive stars set the stage for their successors. Yet the most haunting detail lies in the wave's composition. They're not just hydrogen and helium. Spectrographs reveal traces of oxygen, carbon, and even iron woven into their structures, the nuclear ashes of long-dead stars recycled into these fleeting sculptures. Every crest and trough is a gravestone and a cradle, carrying the remnants of past supernova while shaping the births of future suns. Watching 30 stellar tsunami isn't just observing a cosmic wonder, it's witnessing the life cycle of a galaxy written in waves of gas and fire. And as these ripples roll onward, they carry with them a question. Is this how all star-forming regions evolve, or is the LMC showing us a spectacle unique to its turbulent history? The answer might lie in the next crest or the next supernova about to send shockwaves roaring through the dark. In the cosmic alchemy of the Large Magellanic Cloud, there's a strange chemical imbalance, an overabundance of stars glowing with the telltale orange hue of carbon-rich atmospheres. These aren't just any aging stars, they're cosmic forges pumping out soot-like carbon particles at rates that defy expectations, turning entire swaths of the galaxy into a playground for molecules that shouldn't exist in such quantities. While our Milky Way has its share of carbon stars, the LMC boasts nearly 3 times as many relative to its size, a discrepancy so glaring it suggests this little galaxy cooked up its elements in a radically different kitchen. The secret lies in the LMC's unique metallicity, a fancy term astronomers use to describe how much heavy stuff a star or galaxy contains beyond hydrogen and helium. Unlike the Milky Way, brimming with elements like oxygen, silicon, and iron from generations of star death and rebirth, the LMC is chemically frugal. Its stars formed from gas that was comparatively pristine, richer in hydrogen but poorer in heavier elements. This poverty turns out to be carbon's golden ticket. In low metallicity stars, the nuclear fusion process favors carbon production over oxygen during a star's late-life helium-burning phase. It's like tweaking the recipe of a cake: reduce certain ingredients, and others rise to dominance. But metallicity alone doesn't explain the carbon star bonanza. The LMC's star-forming history plays a pivotal role. While big galaxies like ours churn out stars at a steady clip, the LMC experiences frenetic bursts of star birth followed by long droughts. These erratic cycles mean whole generations of stars reach their carbon-producing phases around the same time, creating temporary surges in carbon enrichment. Imagine a forest where all the trees shed their leaves simultaneously. The ground would be buried under a single, overwhelming layer. That's what happens in the LMC, only with carbon dust instead of autumn foliage. The real kicker: carbon stars aren't just passive factories, they're celestial distributors. As these stars age, their powerful stellar winds carry carbon atoms into interstellar space, seeding future generations of stars and planets with raw materials for organic chemistry. In the LMC's carbon-rich environment, this has startling implications. Protoplanetary disks forming today might contain far more carbon-based molecules than their Milky Way counterparts, raising tantalizing questions about the building blocks available for potential life. Yet the mystery deepens when we look at individual stars. Some LMC carbon stars show bizarrely high levels of lithium, an element usually destroyed in stellar interiors. One theory suggests these stars might be dredging up material from layers where nuclear reactions created lithium as a byproduct. Others propose the lithium comes from cosmic rays slamming into carbon atoms in space, a process that would require densities of carbon we've never observed elsewhere. This chemical oddity isn't just a quirk, it's a window into how small galaxies evolve differently from their larger cousins. The LMC's carbon stars are time capsules, preserving a record of how elements circulated when the universe was younger and galaxies less enriched. Every orange-tinged giant in this dwarf galaxy is a reminder that the cosmos doesn't follow a single blueprint. It experiments, improvises, and sometimes, like a chef with a heavy hand, pours in way more carbon than the recipe calls for. And in doing so, it might just be setting the table for forms of chemistry we've yet to discover. Nestled in different corners of the Large Magellanic Cloud, two supernova remnants, N132d and N49b, act as cosmic factories, churning out heavy elements and cosmic rays at staggering rates. Though they share the same violent origin story, the way these stellar corpses operate couldn't be more different. One is a textbook example of a core collapse explosion, while the other hides evidence of a far rarer, more apocalyptic death. Together, they showcase the universe's two primary methods of stellar destruction and how each leaves behind a unique chemical fingerprint. Take N132d first. This 2,000-year-old remnant glows like a celestial neon sign, its tangled filaments rich with oxygen, neon, and sulfur, the telltale elements forged in the heart of a massive star before its core imploded. X-ray telescopes reveal a shockwave still expanding at over 5,000 kilometers per second, heating surrounding gas to millions of degrees. But what really sets N132d apart is its particle accelerator effect. As the shockwave plows through interstellar space, it traps charged particles in magnetic fields, whipping them to near light speeds. These cosmic rays bombard the surrounding nebula, triggering secondary radiation that paints the remnant in eerie, high-energy hues. It's a natural hadron collider operating on a scale no human machine could ever replicate. Now contrast that with N49b, its enigmatic neighbor. At first glance, it shares similarities: expanding debris, glowing filaments, even a pulsar spinning at its heart. But spectral analysis reveals a critical difference: a bizarre overabundance of titanium and chromium, elements typically scarce in core collapse remnants. This anomaly points to a far more exotic explosion mechanism, a Type Ia supernova, where a white dwarf star detonated after siphoning too much mass from a companion. Unlike the messy, asymmetrical death of N132D's progenitor, N49B's explosion was a runaway thermonuclear blast so precise it's used as a cosmic yardstick across the universe. The way these remnants enrich their surroundings diverges dramatically. N132D acts like a shotgun blast, spraying heavy elements unevenly into space. Its filaments show pockets of extreme enrichment right next to near-pristine gas, as if the explosion couldn't thoroughly mix its ashes. N49B, by contrast, distributed its elements with eerie uniformity, a hallmark of Type Ia explosions, where nuclear burning propagates at near-perfect efficiency. This difference matters profoundly for planetary formation. Solar systems born from N132D's debris might inherit wildly varying chemical compositions, while those seeded by N49B's ejector would get a more balanced elemental diet. Yet both remnants share one haunting trait: their pulsars don't behave as expected. N132D's neutron star spins slower than models predict, as if bogged down by some unseen force, perhaps a fallback disk of material that collapsed back onto it after the explosion. N49B's pulsar, meanwhile, races at a blistering 60 milliseconds per rotation while emitting gamma rays in unpredictable bursts. Some theorists suggest it might be a magnetar in disguise, its magnetic field lines twisting and snapping like overstressed rubber bands. These misbehaving stellar corpses remind us that even well-studied supernova types can leave behind surprises that upend our assumptions. The most tantalizing revelation comes from their cosmic ray outputs. N132D generates protons and light nuclei typical of core collapse shocks, but N49B's rays carry an unexpected bonus antimatter. Satellite detectors have spotted positrons, anti-electrons, streaming from its direction, possibly created when the Type Ia explosion's radioactive byproducts decayed in flight. If confirmed, this would make N49B one of the few known natural antimatter sources in our galactic neighborhood, a potential fuel depot for future interstellar travelers, assuming we could harness it. What makes studying these twin remnants so valuable isn't just their individual oddities, but the way they complement each other. Together, they form a complete picture of stellar death's duality, one violent and messy, the other precise and clean. Both seed the cosmos with the ingredients for planets and life, but through entirely different recipes. And as their shockwaves continue to expand, they serve as living laboratories, showing us how the universe transforms chaos into creation, one exploding star at a time. Stretching across the void like a celestial umbilical cord, an almost invisible river of hydrogen gas flows between the Large and Small Magellanic Clouds, a 75,000 light-year filament so vast it could wrap around our Milky Way twice. This intergalactic bridge, composed primarily of cold atomic hydrogen, represents one of the most dramatic pieces of evidence for the violent gravitational dance these two galaxies have performed for billions of years. Unlike the crisp, defined structures within galaxies, this stream is diffuse and fractured, a ghostly echo of past collisions written in gas rather than stars. The leading theory suggests this bridge formed during a particularly close encounter roughly 200 million years ago, when the Small Magellanic Cloud veered perilously near its larger neighbor. As the galaxies grazed each other, their mutual gravity played a cosmic game of tug-of-war, ripping gas from both systems and stretching it across the intergalactic void. Computer simulations show this process in stunning detail. The moment when tidal forces overcome a galaxy's gravitational binding energy, peeling away its outermost gas like orange skin. What makes the LMC's case unique is the sheer volume of material displaced enough hydrogen to form billions of stars, left suspended between the galaxies like dew on a spider's web. But the bridge holds deeper mysteries than its origin. Spectroscopic analysis reveals bizarre clumping patterns, with some gas pockets denser than expected for freely flowing material. One possible explanation involves dark matter. If the Magellanic Cloud's invisible halos extended tendrils during their encounter, these could have acted as gravitational scaffolds, gathering stray hydrogen into thicker strands. Another oddity, the bridge's chemical composition shows unexpected traces of heavier elements mixed with pristine hydrogen, suggesting supernova explosions within the galaxies may have polluted the stream with metals long after its formation. Perhaps most fascinating is the bridge's future. Rather than dissipating, much of this gas appears to be flowing back toward the LMC, pulled by its stronger gravity. Some astronomers speculate we're witnessing the early stages of galactic recycling, a process where stolen material eventually returns home to fuel new generations of stars. If true, intergalactic bridges like this might serve as cosmic conveyor belts, shuttling raw materials between galaxies on timescales spanning billions of years. Yet the greatest surprise came when radio telescopes detected faint but organized magnetic fields threading the bridge far stronger than predicted for such diffuse material. These fields might act as cosmic highways, channeling charged particles along specific paths and potentially influencing how gas eventually falls back into the galaxies. It's a reminder that even in the seeming emptiness between galaxies, invisible forces are at work, shaping the universe on scales we're only beginning to understand. This ethereal ribbon of gas isn't just debris from a past encounter. It's an active participant in the ongoing story of these two galaxies, a silent witness to forces that can stretch the fabric of reality itself. Among the ancient stellar populations of the Large Magellanic Cloud, where astronomers expect to find only aging red giants and dim, cooling embers, something impossible gleams, clusters of youthful blue stars blazing with the intensity of stellar newborns. These aren't misplaced stragglers, they're celestial rule breakers, shining defiantly in regions otherwise dominated by stars billions of years old. The mystery isn't just their presence, it's how they got there, challenging everything we know about stellar evolution timelines and the LMC's turbulent history. Take the blue stragglers in globular cluster NGC 205-8. By all rights, this dense swarm of stars should be a retirement community. Its members formed over 12 billion years ago in the early universe. Yet scattered among its crimson elders are stars burning hot and blue, their surfaces sizzling at temperatures rivaling stars a fraction of their age. The leading theory, cosmic vampirism. In the tight quarters of a globular cluster, stars often orbit in binary pairs. When one star expands into a red giant, its hungry companion can siphon off fresh hydrogen from its outer layers, rejuvenating itself with stolen fuel. The result is a star that appears decades younger than its birth certificate claims, a celestial Benjamin Button burning bright on borrowed time. But the plot thickens when we examine isolated blue stars in the LMC's halo regions so sparse that stellar collisions are vanishingly rare. Here, another mechanism must be at work. Spectroscopic analysis reveals some of these outliers contain abnormally high levels of helium and nitrogen, fingerprints of stars that have undergone internal mixing so extreme it's like shaking a snow globe until the flakes redistribute. Normally, a star's convection zones keep nuclear-burned material trapped deep in its core, but for certain mid-sized stars in the LMC, rotation or magnetic fields might stir the pot violently enough to bring fresh hydrogen down to fusion zones while dredging up helium byproducts, effectively extending their blue phase lifespans through stellar alchemy. The real curveball comes from star-forming regions where these blue anomalies cluster unexpectedly. In the LMC's outer reaches, far from the hustle of active nebulae, Hubble has spotted pockets of young, massive blue stars with no nearby gas clouds to explain their birth. One provocative explanation suggests these might be runaway stars, stellar bodies flung from violent environments like the Tarantula Nebula by gravitational slingshots or supernova kicks. Traveling at hundreds of kilometers per second, they could have migrated over millions of years before igniting nuclear fusion en route, planting blue flags in territories that hadn't seen starbirth in eons. Yet the most tantalizing possibility involves the LMC's cannibalistic past. If this dwarf galaxy absorbed smaller companions throughout its history, as its distorted shape suggests it could have captured young star clusters from defunct satellites, dispersing them unevenly across its territory. These stellar immigrants would then appear anomalously youthful compared to native populations, creating pockets of blue where theory predicts only red should glow. Supporting this idea, chemical analysis shows some blue stars in ancient regions share elemental abundances with known LMC satellite remnants, like fingerprints matching a suspect to a crime scene. What makes these blue dwarfs more than just cosmic curiosities is their role in galactic archaeology. Each one carries clues, whether through composition, motion, or location, about the LMC's volatile history of collisions, tidal interactions, and internal upheavals. They're celestial stopwatches, marking moments when the galaxy's steady aging was punctuated by bursts of violent rejuvenation. And as we decode their origins, we're forced to confront an uncomfortable truth. In the cosmos, age might just be a number, one that gravity, chance, and stellar drama can rewrite at will. The Large Magellanic Cloud hides an invisible shimmer, not of light but of gamma rays, the universe's most energetic radiation. Unlike the pinpoint bursts we see from pulsars or supernova, this glow smears across the galaxy like fog, a diffuse haze of high-energy photons with no obvious source. It's as if the entire LMC is bathed in some unseen particle accelerator, pumping out gamma rays from every direction at once. What's powering this eerie luminosity? The answer could rewrite our understanding of dark matter, stellar evolution, or even the fundamental laws of physics. At first glance, the fog seems like it should be simple to explain. Gamma rays typically come from extreme cosmic events, collapsing stars, annihilating antimatter, or particles racing near light speed. The LMC hosts plenty of these: microquasars, supernova remnants, and massive young stars whose winds collide violently. Yet when astronomers tally up all known gamma sources, they account for less than half the observed glow. The rest emerges from nowhere, saturating the space between stars with unexplained energy. One tantalizing theory points to dark matter, the invisible substance making up most of the universe's mass. If certain hypothetical dark matter particles exist, they might annihilate upon collision, dissolving into gamma rays. The LMC's dense dark matter halo could be a prime site for these interactions, turning the entire galaxy into a faintly glowing beacon of particle physics. Supporting this idea, the gamma fog's distribution doesn't perfectly match visible matter, instead tracing a smoother, more spherical pattern reminiscent of predicted dark matter profiles. But there's a competing explanation, one just as revolutionary. The glow might come from thousands of hidden cosmic accelerators too faint to spot individually. Imagine a galaxy teeming with microscopic pulsar wind nebulae, dim supernova shocks, or even a new class of substellar objects that convert magnetic energy into gamma rays. The LMC's unique environment, lower metallicity, stronger tidal forces, could make it a breeding ground for such exotic emitters. Some researchers speculate that aging, rapidly spinning neutron stars called millisecond pulsars might be the culprits, their cumulative output creating a synthetic fog. The real enigma lies in the gamma ray's energy signature. Most of the fog clusters around 1 to 3 giga-electronvolts, a sweet spot that neither fully matches dark matter models nor aligns neatly with known astrophysical sources. It's as if the universe is teasing us with a puzzle piece that fits multiple boards. Adding to the mystery, recent observations show the fog isn't static. In regions with intense star formation, gamma-ray intensity spikes, suggesting a link to young, massive stars. Yet even when accounting for these hotspots, the background glow persists stubbornly uniform. This isn't just an LMC curiosity. If the fog stems from dark matter, its detection here would be a roadmap for finding similar halos elsewhere. If it's from undiscovered astrophysical sources, it implies our catalogues of gamma emitters are woefully incomplete. Either way, the glow represents a frontier, an energy reservoir we've barely begun to tap into. Future telescopes might crack the case by spotting subtle fluctuations in the fog's distribution or identifying new point sources buried in the noise. Until then, the gamma-ray haze remains a cosmic Rorschach test. What we see in it depends on which theories we bring. And as we stare into this high-energy mist, we're reminded that sometimes the universe's boldest mysteries don't announce themselves with flashes or explosions, but with a quiet, pervasive glow that refuses to be ignored. Among the ghostly remnants of dead stars in the Large Magellanic Cloud, two planetary nebulae gleam like cosmic stained glass, SMP-LMC 11 and SMP-LMC 62. At first glance, they could be twins, their delicate shells of glowing gas expanding gracefully into space. But peer closer, and their differences become as stark as night and day. These celestial afterimages tell wildly divergent stories of how stars live, die, and scatter their ashes across the universe. SMP-LMC 11 glows with an ethereal blue-green hue, its intricate filamentary structure resembling frosted glass. This beauty stems from its composition, oxygen-rich gas excited by the ultraviolet radiation of its exposed stellar core. That tiny, searing remnant, now a white dwarf, was once a star much like our Sun, gently shedding its outer layers over millennia as it transitioned into retirement. The nebula's symmetrical shape suggests a relatively peaceful demise, with stellar winds carving this cosmic bubble almost perfectly round. But the real surprise lies in its chemistry. Spectral analysis reveals startlingly high levels of neon and argon elements typically forged deeper in a star's core than planetary nebulae usually dredge up. This hints at a far more dramatic past. The star may have undergone violent thermal pulses in its final millennia, convulsions that mixed deep interior material to the surface like a geyser spewing buried treasures. Now contrast that with SMP-LMC 62, its reddish tendrils twisting through space like smoke from an extinguished candle. Here, the dominant glow comes from nitrogen and hydrogen, the outer layers of a star that was significantly heavier than SMP-LMC 11's progenitor. This star lived fast and died hard. Born with 3 times the Sun's mass, it burned through its fuel recklessly, swelling into a red giant before expelling its envelope in furious eruptions. The nebula's chaotic structure reflects this turbulent end, its asymmetrical lobes and knots betraying the presence of powerful magnetic fields or a companion star that disrupted the death throes. The most intriguing clue, carbon soot. Unlike its oxygen-rich counterpart, SMP-LMC 62's dust lanes are packed with complex carbon molecules, the same building blocks that form planets and life. This star didn't just die, it seeded the cosmos with organic potential. The dichotomy between these two nebulae reveals a fundamental truth about stellar life cycles: mass is destiny. A star's initial weight dictates not just how it lives, but how it dies and what legacy it leaves behind. Lower mass stars like SMP-LMC 11's progenitor tend to expire with relative decorum, their gently expelled gas rich in oxygen from steady nuclear burning. But heavier stars like SMP-LMC 62's forebear rage against the dying of the light, their deaths enriching space with carbon and nitrogen through violent convulsions. Each nebula is a fossil record of its star's internal chemistry, frozen in the act of dispersal, yet both share an ironic fate. The very elements they've released, oxygen here, carbon there, will someday mix in the LMC's swirling gas clouds. Future stars born from this blend may inherit a more varied chemical palette than their ancestors ever did. In death, these stellar opposites become collaborators, their once distinct signatures merging into the raw materials for new worlds. And as we study their differences, we're really seeing two sides of the same cosmic coin: the quiet resignation of one star's end and the explosive rebellion of another's, each beautiful in its own way. Most galaxies scatter their supernova evenly, like fireworks bursting randomly across a night sky. But the Large Magellanic Cloud writes its explosive history with a cosmic bias. Recent stellar detonations overwhelmingly favor its northeastern quadrant, painting a lopsided map of stellar deaths. This isn't just statistical noise, it's a glaring anomaly, one that hints at hidden forces reshaping the galaxy behind the scenes. Zoom in on the pattern and the clustering becomes undeniable. Over the past 5 centuries, a blink in cosmic time, nearly 70% of recorded supernova erupted within a wedge-shaped region stretching from the Tarantula Nebula to the galaxy's outer fringes. Some of these explosions left behind pulsars racing through space at breakneck speeds, their trajectories tracing back to this same active zone. Meanwhile, the LMC's southwestern hemisphere remains eerily quiet, its stellar populations aging without the violent punctuation of supernova. This imbalance persists across supernova types. 2 core collapse explosions from massive stars and thermonuclear detonations of white dwarfs both show the same uneven distribution. What could drive such asymmetry? The leading suspect is the LMC's tortured gravitational history. As the galaxy orbits the Milky Way, tidal forces don't pull evenly across its structure, they yank hardest on the side nearest our galaxy. This differential stretching, combined with past collisions with the small Magellanic Cloud, may have triggered waves of star formation predominantly in one hemisphere. Supporting this theory, the supernova-rich northeast coincides with the galaxy's most active star-forming regions, where stellar birth rates peaked 20 to 40 million years ago, perfect timing for the resulting massive stars to now reach their explosive ends. But there's a twist. Detailed star count surveys reveal the LMC's stellar population isn't actually lopsided enough to explain the supernova skew. The quiet regions host plenty of potential supernova progenitors, they're just not detonating at expected rates. This discrepancy points to environmental factors beyond simple star distribution. Some researchers propose the Southwest's interstellar medium might be oddly efficient at stabilizing aging stars, perhaps through weaker stellar winds or lower rates of binary interactions that could trigger premature explosions. Alternatively, the Northeast's intense radiation fields from young stars might stress nearby aging stars, hastening their demise like cosmic peer pressure. The wild card: dark matter. If the LMC's invisible halo is lumpy or asymmetrical, as some observations suggest, its uneven gravity could subtly influence where stars live and die. Denser dark matter concentrations might compress gas clouds enough to birth more massive stars in specific zones, or perhaps distort the internal dynamics of aging stars to make them explode more readily. It's a reminder that supernova aren't just about the stars themselves, they're products of their environment, from the galactic scale down to local stellar neighborhoods. This lopsided carnage has cascading effects. Every supernova enriches its surroundings with heavy elements and sends shockwaves rippling through nearby gas clouds. The Northeast's hyperactivity means it's essentially fertilizing itself, creating ideal conditions for even more massive stars and future supernova to form. Meanwhile, the Southwest's relative calm allows older stars to dominate, their gentle winds releasing fewer heavy elements back into the galactic ecosystem. Over billions of years, this could split the LMC into 2 chemically distinct hemispheres, a division written in the very elements that compose new stars and planets. Perhaps most intriguing is what this teaches us about galactic archaeology. The supernova distribution isn't just a present-day curiosity. It's a fossil record of past disturbances, a way to reconstruct the LMC's violent gravitational encounters long after visible scars fade. Each explosion cluster is a timestamp marking when cosmic turbulence stirred this small galaxy, shaping the stellar populations we see today. And as we decode this asymmetric pattern, we're glimpsing a fundamental truth. Even in something as catastrophic as stellar death, location isn't random, it's history echoing through space. 2,000 years ago, a star in the Large Magellanic Cloud tore itself apart with such violence that its shattered remains are still racing through space today, a runaway supernova remnant designated N63A. Unlike most stellar explosions that expand symmetrically into the void, this one moves with purpose, plowing through interstellar gas like a cosmic speedboat, leaving behind a glowing bow shock that ripples across 40 light-years of space. What makes this remnant extraordinary isn't just its speed, it's the stunning clarity with which we can witness the physics of its motion, a real-time demonstration of how stellar death shapes galactic ecosystems. At the heart of N63 lies a neutron star, the dense corpse of the original star, hurtling forward at over 400 kilometers per second. As this cosmic cannonball barrels through surrounding gas clouds, it behaves like a pebble thrown into a pond, except instead of water, the pond is made of diffuse hydrogen and the ripples glow in X-rays. The bow shock takes shape where the neutron star's powerful magnetic field and particle winds slam into stationary interstellar material, compressing and heating it into a luminous arc. This structure isn't static. It morphs constantly with turbulent eddies and finger-like protrusions revealing the chaotic interplay between the remnant's energy and the galaxy's ambient medium. But here's where the physics gets weird. The bow shock's shape defies simple fluid dynamics. Instead of a smooth curve, it's jagged and asymmetrical, with one side flaring dramatically wider than the other. Radio telescope images show magnetic fields tangled like spaghetti within the shock front, suggesting the neutron star isn't just moving, it's spinning wildly, its rotation axis tilted at an oblique angle to its direction of travel. This mismatch turns the shock zone into a cosmic whirlpool, where magnetic turbulence redirects particles in erratic directions. Some electrons get whipped to near-light speeds within these fields, emitting synchrotron radiation that paints the shock in eerie blue hues across certain wavelengths. The remnant's wake tells an equally compelling story. Behind the neutron star, a trail of heated gas stretches like a comet's tail, dotted with dense knots where supernova debris has mixed with interstellar material. These knots act as time capsules. Some retain pristine ejecta from the explosion, rich in silicon and iron, while others have absorbed so much ambient hydrogen they've cooled enough to form molecular compounds. It's a snapshot of chemistry in action, showing how supernovas seed galaxies with both raw elements and the energy to jumpstart new reactions. What caused this stellar corpse to run away in the first place? The leading theory points to an asymmetric explosion. When the original star went supernova, the collapse might have ejected material more forcefully in one direction, kicking the newborn neutron star opposite that vector like a rocket recoiling from its exhaust. Supporting this idea, spectroscopic studies reveal that iron-rich ejecta on one side of the remnant move significantly faster than debris elsewhere, as if that quadrant received an extra thrust during detonation. Alternatively, the neutron star might have been born in a binary system, its partner either vaporized in the blast or flung away as a rogue star, a cosmic divorce leaving one party speeding into the void. N63A's greatest lesson might be about galactic ecology. As it carves through the LMC's gas clouds, it's not just destroying, it's creating. The shock front's pressure triggers star formation in its path, compressing nearby hydrogen until gravity takes over. Infrared telescopes have spotted protostars lining the rim of the bow shock, their births directly linked to the remnant's passage. It's stellar reincarnation on a cosmic scale, one star's death giving rise to the next generation. And as we watch this runaway remnant charge onward, we're reminded that in the LMC, even destruction moves with purpose, weaving new stories from the ashes of the old. The Large Magellanic Cloud isn't just our cosmic neighbor. It's on a direct collision course with our galaxy, barreling toward a merger that will rewrite the night sky in ways beyond imagination. In roughly 2.4 billion years, this dwarf galaxy will slam into the Milky Way, triggering a celestial transformation so profound it will reshape both galaxies forever. This isn't a quiet cosmic rendezvous, it's a full-scale gravitational upheaval, a dance of destruction and creation that will leave neither galaxy recognizable. Picture this: the first gravitational ripples warp the Milky Way's pristine spiral arms long before impact. As the LMC closes in, its immense dark matter halo, a ghostly shroud 10 times heavier than its visible stars, starts plowing through our galaxy's outer reaches. Tidal forces shred delicate stellar streams and dwarf satellites orbiting the Milky Way, scattering them like leaves in a hurricane. Meanwhile, the LMC's own structure distorts under counterforces, its stars stretched into luminous tendrils that wrap around our galactic center in slow motion. When the true merger begins, chaos erupts. The LMC's dense core, home to the Tarantula Nebula's stellar fireworks, plunges through the Milky Way's disk, igniting shockwaves that compress gas clouds into sudden starbursts. Night skies from future Earth, if it still exists, would witness terrifying beauty, new star clusters flaring to life like matches struck in the dark, while supernova detonate at rates unseen for billions of years. The Milky Way's orderly spiral transforms into a messy, glowing pancake of stirred-up stars, its symmetry obliterated, but the real drama unfolds in the gravitational aftermath. As the LMC's remnants settle into orbit around the Milky Way's supermassive black hole, they drag entire star clusters with them, creating swirling stellar whirlpools. Some models suggest this merger could awaken our dormant central black hole, feeding it enough material to temporarily shine as a quasar, a beacon visible across the universe. Meanwhile, the collision flings stars into unpredictable trajectories. Our solar system, if it survives, might find itself hurled into the galactic halo or catapulted perilously close to the turbulent core. This collision won't just reshape structure, it'll rewrite chemistry. The LMC's metal pore gas will dilute the Milky Way's enriched interstellar medium, altering the recipe for future stars. Yet its carbon-rich stellar nurseries might also seed new organic molecules across our galaxy, potentially influencing the emergence of life in distant epochs. The ultimate legacy, a hybrid galaxy, no longer a neat spiral nor a messy dwarf, but something entirely new. Future astronomers might gaze up at a night sky where familiar constellations have scattered, replaced by a brilliant, irregular haze of merged starlight. And somewhere in that glow, the remnants of the LMC will endure, not as a separate entity, but as strands of stars woven into our galaxy's DNA, a silent testament to the universe's relentless transformations. The Tarantula Nebula isn't just a stellar nursery, it's a time capsule, preserving conditions so extreme they haven't been commonplace since the universe's fiery infancy. This sprawling cauldron of gas and young stars mirrors the environments that birthed the first stellar generations, offering astronomers an unprecedented window into how the cosmos transformed darkness into light. At the nebula's core, radiation and stellar winds reach intensities rarely seen in the modern universe. The young, massive stars here are so luminous their ultraviolet output outshines entire galaxies, ionizing surrounding hydrogen into a plasma so hot it glows like a neon sign across 10,000 light-years. These conditions, once universal in the chaotic aftermath of the Big Bang, are now nearly extinct elsewhere, making the Tarantula one of the few places where we can witness the physics of primordial starbirth firsthand. Recent studies reveal even deeper parallels. the nebula's gas clouds exhibit strikingly low metallicity, their chemical composition skewed toward hydrogen and helium with trace amounts of heavier elements. This matches theoretical models of the early universe before generations of supernova enriched the cosmos with elements like carbon and oxygen. In this sense, the Tarantula's star-forming regions act like cosmic islands, preserving pockets of pristine gas akin to those that birthed the universe's first stars. But the most jaw-dropping similarity lies in the stellar products themselves. The Tarantula churns out stars of staggering mass, some exceeding 300 solar masses, rivaling the theoretical upper limits of the earliest stellar behemoths. These monsters burn ferociously and die young, their life cycles compressed into mere millions of years. Their existence suggests that the same processes governing star formation 13 billion years ago, where gravity overpowered weaker radiation pressure in metal-poor gas, are still operational in this corner of the LMC. What makes these modern primordial stars invaluable is the detail we can observe. Unlike their ancient counterparts long vanished into black holes or supernova, the Tarantula's giants are caught in the act. Telescopes like JWST detect their outflows, revealing how their fierce winds interact with surrounding material. Some show evidence of dark zones around them, cavities where radiation pressure clears gas so completely it halts further star formation nearby. This phenomenon, predicted in models of early universe star factories, was only confirmed thanks to the Tarantula's extreme environment. Yet the nebula adds twists to the primordial recipe. Its stars form in clusters rather than isolation, and their winds sometimes trigger secondary star birth, something likely rare in the early universe's sparser gas distributions. These differences remind us that while the Tarantula is our best local analog, it's not a perfect replica. It's a hybrid, part relic, part modern marvel, blending the universe's oldest star-forming secrets with the dynamic complexity of a mature galaxy. By decoding these nuances, astronomers are rewriting the story of cosmic dawn. The Tarantula's lessons suggest the first stars may have been more diverse and their environments more varied than simulations predicted. Every massive star born here is a clue, every shockwave rippling through its gas a whisper from the past. And as we study this turbulent, luminous time machine, we're not just peering into the LMC, we're glimpsing the universe's first moments of light. LMC X-3 isn't just consuming its stellar companion, it's playing with its food. Recent high-resolution observations reveal this black hole's accretion disk doesn't spiral inward smoothly like most others. It pulses erratically, flickering between states of gluttony and starvation with no discernible pattern. 1 month, it devours gas at a rate that should make its X-ray emissions outshine entire galaxies. The next, it falls eerily silent, as if an invisible hand has shut off the cosmic faucet. This isn't normal black hole behavior, it's a feeding frenzy with no rulebook, and astronomers are scrambling to decode what's really happening behind the event horizon. The key to this mystery lies in the disk's bizarre structure. Normally, accretion disks flatten into orderly planes as they approach a black hole like water circling a drain. But LMC X-3's disk warps unpredictably, forming transient bulges and gaps that resemble a vinyl record left too close to a heat source. Some sections tilt nearly vertically, exposing their inner edges to direct view before suddenly collapsing back into alignment. These distortions aren't just cosmetic, they dramatically alter how material falls inward. When the disk buckles, gas streams collide at oblique angles, creating shock waves that heat the plasma to temperatures beyond what standard models predict. X-ray telescopes catch these moments as sudden flares, spikes so intense they temporarily blind detectors. Even stranger is the black hole's apparent indigestion. About 30% of the inflowing gas doesn't vanish beyond the event horizon. It gets vomited back into space as bipolar jets. Normally, jets emerge steadily from a black hole's poles, but LMC X-3's outbursts arrive in hiccup-like bursts, each lasting precisely 17 minutes before cutting out abruptly. The leading theory suggests the black hole's spin axis wobbles like a top losing momentum, causing its magnetic field lines to twist until they snap, catapulting trapped particles outward. Supporting this, radio telescopes detect spiraling polarization patterns in the jets, signatures of a magnetic field under extreme torsion. The companion star adds another layer of chaos. Unlike typical black hole binaries where the donor star passively surrenders material, LMC X-3's partner fights back. Spectroscopic data shows its stellar winds aren't uniform breezes. They're gusty squalls that vary by a factor of 10 in density over days. When a dense clump hits the accretion disk, it triggers chain reactions. Shock waves propagate inward, temporarily overfeeding the black hole before clearing out the delivery pipeline. It's like trying to drink from a fire hose that keeps switching between a trickle and a deluge. What makes these observations revolutionary isn't just the black hole's antics, it's what they reveal about accretion physics under extreme conditions. LMC X-3 operates at nearly 50% of the theoretical maximum feeding rate for its size, a zone where conventional models break down. At these thresholds, radiation pressure should blow away in falling gas, yet somehow, this system keeps finding ways to shove more material inward. Some theorists speculate the disk's warps create shadowed regions where gas can slip past the radiation barrage, like cosmic smugglers evading searchlights. Others propose the black hole's gravity bends spacetime so severely that photons get trapped in orbits, reducing their outward push. The implications ripple far beyond this one system. If LMC X-3's feeding mechanisms are common but previously undetected, they could explain why some black holes seem to grow faster than models allow. Its erratic jets might also shed light on mysterious transient events observed in distant galaxies, flares once attributed to supernova that could instead be black holes hiccuping plasma across interstellar space. Every bizarre fluctuation in this system forces us to reconsider what we thought we knew about how darkness consumes light, and how sometimes it sends it screaming back into the void. The Large Magellanic Cloud doesn't just host stars, it keeps a chemical diary scribbled in the elemental signatures of its gas clouds and stellar atmospheres. These aren't random notes, they're a galactic autopsy report revealing how generations of stars lived, died, and recycled their remains into the cosmos. What makes the LMC's chemical fingerprint so extraordinary isn't just what elements are present, it's their stark imbalances. Patterns that would be bizarre anywhere else but here make perfect sense. Take the carbon conundrum first. As we've seen, the LMC overflows with carbon-rich stars, their atmospheres sootier than a chimney sweep's gloves. Normally, oxygen outpaces carbon in galaxy chemistry. It's the universe's third most common element after hydrogen and helium. But in the LMC's low metallicity environment, the nuclear equations skew differently. Smaller stars here fuse helium into carbon more efficiently, while the reactions that normally convert carbon into oxygen sputter like damp firecrackers. The result, a galaxy where carbon stars outnumber oxygen-rich ones 3-to-1, their stellar winds peppering interstellar space with organic precursors. It's as if the universe tilted a cosmic scale, favoring the building blocks of life over the minerals of rock. Now flipped to the heavy elements, the cosmic afterthoughts like europium, barium, and lead. These rare metals typically form in two ways: the slow neutron capture process in aging red giants, or the rapid neutron capture during supernova. The LMC's stellar graveyards show both pathways in overdrive, but with a twist. Its globular clusters contain stars sporting europium levels 10 times higher than Milky Way counterparts, a signature of prolific neutron star mergers, where collapsing stellar cores become element factories. Yet elsewhere, like in supernova remnant N132d, heavy elements appear diluted, as if the explosions here couldn't quite squeeze every possible atom from their fuel. This duality suggests the LMC's chemical enrichment wasn't steady, but chaotic periods of intense neutron bombardment followed by quieter eras where lighter elements dominated. The most revealing clues come from comparing stellar generations. Young, massive stars in the Tarantula Nebula show oddly clean compositions, their atmospheres nearly pristine, as if they formed from gas barely touched by previous supernova. Meanwhile, older stars orbiting the galaxy's fringes were their heavy elements like gaudy jewelry, their spectra spiked with metals forged in the early universe's violent nurseries. This disparity paints a picture of a galaxy that didn't mix its stellar ashes evenly. Instead, supernova in the LMC's chaotic past must have blasted their debris in narrow jets, enriching some regions while leaving others strangely untouched. Then there's the helium paradox. In most galaxies, helium accumulates gradually as stars fuse hydrogen over eons. But the LMC sports pockets of gas with helium levels so high they rival stellar cores, up to 40% by mass compared to the usual 10% in interstellar space. This isn't just aging stars leaking helium. It's evidence of catastrophic stripping events where entire stellar layers were ripped away by tidal forces or supernova shocks. These helium-rich zones become cosmic petri dishes, altering how new stars ignite. With less hydrogen to dilute it, helium changes fusion rates, letting stars burn hotter and die younger than they would in richer chemical soups. What emerges from this elemental tapestry is a story of galactic adolescence. The LMC never settled into the balanced chemistry of mature galaxies like ours. Its starbursts and quiet spells, its lopsided mergers and turbulent orbits, they all left marks in the periodic table's language. Every carbon star is a protest against cosmic convention. Every europium spike a timestamp of ancient collisions. And as we decode these signatures, we're not just reading a single galaxy's history. We're glimpsing the raw, unfiltered processes that built the universe itself. Stretching across a staggering 600,000 light-years of intergalactic space, the Magellanic Stream arcs behind the Large and Small Magellanic Clouds like a ghostly contrail, a river of hydrogen gas so tenuous it emits no visible light, yet so massive it contains enough material to build millions of stars. For decades, this cosmic ribbon puzzled astronomers. How could two small galaxies, barely 1% the Milky Way size, produce such an enormous structure? Recent supercomputer simulations have cracked the case, revealing a celestial tug-of-war more violent than anyone imagined, one where dark matter, galactic collisions, and tidal forces all conspired to rip these dwarf galaxies apart. The breakthrough came when astrophysicists modeled the cloud's orbits backward in time, factoring in the Milky Way's gravitational pull and, crucially, the invisible drag of dark matter halos surrounding all three galaxies. These simulations revealed a dramatic scene from 2.5 billion years ago. The Small Magellanic Cloud wasn't always our satellite galaxy. It was a free-flying rebel that made a catastrophic close pass by the Large Magellanic Cloud. As the smaller galaxy zipped within 75,000 light-years of its neighbor, their mutual gravity triggered a cosmic catastrophe. The LMC's more substantial dark matter halo acted like an invisible wrecking ball, shearing gas from the SMC's outer layers while simultaneously losing some of its own hydrogen to the chaos. But here's where the physics gets wild. The stolen gas didn't just drift away, it got stretched into filaments by competing gravitational forces. The Milky Way's immense gravity pulled one way, the LMC's dark matter tugged another, and the SMC's desperate hold on its remaining material created turbulent eddies in between. This three-way gravitational arm wrestling match produced the stream's complex braided structure, with denser knots marking regions where gas clouds collided like cars in a celestial traffic jam. Radio telescopes have since confirmed these simulations, detecting faint shock fronts within the stream that match predicted collision sites down to the light year. The most astonishing revelation: the stream isn't just debris, it's a fossil record of galactic suffering. Spectroscopic analysis shows its gas bears distinct chemical signatures from both clouds, layered like tree rings. Deeper segments contain pristine hydrogen with almost no heavy elements, ripped from the SMC's untouched outer fringes. Closer to the Milky Way, the gas is laced with oxygen and silicon, ejecta from LMC supernova that was already enriched before being torn loose. This stratification proves the stream formed in multiple epochs, with later close encounters adding fresh material like layers on a cosmic onion. Now comes the twist that changes everything. For years, astronomers assumed the Magellanic Stream would eventually fall into the Milky Way, becoming mere fuel for future star birth. But the latest data suggests it might be too late. The stream is disintegrating faster than anticipated. ESA's Gaia spacecraft tracked hundreds of stars within the stream, revealing they're not moving uniformly toward our galaxy as predicted. Instead, their orbits suggest the structure is fragmenting, with some sections destined to escape the local group entirely. This means we're witnessing the stream in its death, throws a fleeting cosmic spectacle that future civilizations might never see. Yet even in its demise, the stream holds secrets. Certain segments glow faintly in UV, not from starlight, but from collisions between stream material and the Milky Way's outer halo. These impact zones create shock fronts that excite hydrogen atoms, making them fluoresce like neon signs in a cosmic wind tunnel. Mapping these glow patterns reveals something shocking. The Milky Way's dark matter halo isn't perfectly spherical as assumed, but slightly squashed, its invisible mass distribution warping the stream's path like a funhouse mirror. What began as a simple trail of gas has become astronomy's Rosetta Stone, a key to decoding how galaxies interact, how dark matter sculpts the universe, and how even the smallest cosmic structures can leave the grandest footprints. And as simulations grow more sophisticated, they hint at an even wilder past, the possibility that the Magellanic Clouds weren't always a pair, but were thrust together by some long-ago intergalactic encounter, making their shared stream not just a product of destruction, but a relic of arranged marriage on a cosmic scale. From vanishing stars to rogue black holes, cosmic tsunamis to sideways spinning galaxies, the Large Magellanic Cloud has taken us on a tour of the universe's strangest rule-breakers. This cosmic neighbor, small enough to fit in the Milky Way's shadow, packs more mysteries per light year than anywhere else we've looked. It's a place where stars fake their own deaths, where dark matter clumps like cosmic cottage cheese, and where stellar nurseries mimic the violent dawn of the universe itself. What makes these discoveries so thrilling isn't just their oddity, it's how they rewrite galactic science. Every textbook assumption about how stars form, how galaxies evolve, even how matter behaves in extreme environments gets tossed out the window here. The LMC shouldn't have hypergiant stars defying mass limits, or planetary nebulae with chemical signatures that make no sense, yet they're there, glowing defiantly, daring us to explain them. This little galaxy is like a cosmic laboratory running experiments we didn't approve, showing us phenomena our models never predicted. Think about what that means. If a dwarf galaxy right next door can append so many rules, what else might be hiding in the vast cosmic dark? Are we seeing exceptions, or just the first hints of a universe far stranger than we imagined? The LMC's greatest gift might be humility, reminding us that for all our telescopes and supercomputers, the cosmos still has cards it hasn't revealed. So which mystery hooked you? The runaway supernova remnant racing through space like a cosmic fugitive, the carbon stars turning entire regions into sooty stellar factories. Or maybe the gamma-ray fog that might be dark matter whispering its first detectable clues. Drop your pick in the comments. I'd love to hear which cosmic oddity blew your mind the most. As we close this journey, remember, the LMC isn't just some distant spectacle. It's our partner in a slow-motion galactic dance, a dance that will eventually erase the space between us. 2.4 billion years from now, when these stars collide with our Milky Way, the night sky will transform forever. But for now, this little galaxy stands as both a mirror and a window, reflecting back how much we've learned while showing us how much wonder still waits just beyond the edge of our understanding. The universe isn't just out there, it's next door, twisting the rules, breaking the molds, and inviting us to keep looking up.